Okay, so we're continuing this chapter on statics, and in the first video we talked about how static equilibrium means that the sum of forces in the x direction equals 0, and the sum of forces in the y direction equals 0. And at the end of the video we also introduced the idea that the sum of the torque is equal to 0, torque or moment. I might find myself calling torque moments because in statics class that's how we refer to it. So what we have here is basically a simple beam analysis problem. We have this horizontal beam. The beam itself has weight, and we also have some large object. It happens to be a printing press, but whatever the load may come from. We have a point load here that's, I think it might be cut off here a little at the bottom of my screen, but this says 15,000 kilograms is the mass times g, because we have to multiply by g to find the weight. And then that beam is supported at both ends by this FB and FA. So we want to know what those forces are. That's what we're trying to calculate. What are the forces at support A and support B? So we can calculate this by using those three equilibrium equations. Let's actually start with the third one, that the sum of torque equals 0. So that means that we can choose any point in this system and add up all of the torques caused by the other forces, and they're all going to cancel each other out. Usually when you're looking at a beam type problem, it's simplest to just start on the left side. I think primarily because we just read from left to right. So if we start here, we'll call this point P. If we sum the torque about point P, it will equal 0. So what are the various torques? Well, we have each torque is caused by a force. So we've got this one right here caused by the self-weight of the beam itself, which is applied at the middle of the beam. The beam is 20 meters long, so it's going to essentially be, we can describe it as a point load at the midspan 10 meters over. So we have 1,500 kilograms. Now that's a mass, not a weight. So we have to multiply that by g to turn it into newtons, to turn it into a force. And then we also have to multiply that by the moment arm distance, or the lever arm, which is 10 meters. Now, the sign convention, at least used in our statics textbook, is that clockwise rotation, clockwise moments, are considered to be negative, whereas a counterclockwise rotation or torque is positive. So the self-weight here, this force is acting down, which is going to try to move this beam in a clockwise direction, which we will consider to be negative. So we'll call that negative 1,500 kilograms times g times 10 meters. That's the torque caused by this force right here. Let's move on to the next force, the force from the printing press. That is also going to be going down, which means it's going to be going around this rotation point right here in a clockwise or negative direction. So we're going to subtract 15,000 kilograms times g times its moment arm length. It is located 10 plus 5 is 15 meters away from the axis of rotation, this point P. And then finally, those two forces are going to be resisted by the support. at the extreme end of the beam. So that's going to cause a counterclockwise rotation about that point. So it's a positive torque, and the force is Fb, and the distance is 20.0 meters. So these three torques, this negative torque, and this positive torque, when they're all added together, will equal 0. They're all going to cancel each other out. That's what's meant by equilibrium. So what are the unknowns here? Well, really just this one. That's really our only unknown force, Fb. So we can find Fb just by solving this one equation. So what is Fb equal to? Fb is equal to these. I'm going to leave Fb alone. It's positive. It's going to stay where it is. The other two terms were negative. They're going to move over to the right side of the equation by adding them. So this will become a positive 1500 G times 10 plus 15,000 G times 15. And then we also had this 20 being multiplied by the Fb, so we've got to divide all of that by 20. Okay, so I suppose I've been kind of neglecting to substitute in the value for G. No particular reason. I guess I can do that now. So this is going to be 1500 times 9.8 times 10.0 plus 15,000 times 9.8 times 15 divided by 20. I suppose I should have made that 15.0. I don't want to drop off my sig figs. Okay, so there we go. We've got all of our terms into the equation. All we have to do is plug that into our calculator and solve, and we should find that we get something like 117,600 newtons. And if we round that to, let's see, it looks like 2 significant figures maybe is what we should be taking this to, would be, I suppose if we took it all the way down to 2 significant figures, it would just be about 120 newtons. So looks like I have in my notes 118. I'm not sure why I would have taken that to 3 significant figures when we've clearly got these 5.0 meter distances. So yeah, I'm thinking it looks like maybe this should just be 2 significant figures. 120,000 newtons is the reaction force here at Fb. 120,000 newtons. Okay, so then what is Fa? Well, let's move on to the next slide here. So one of our other equilibrium equations was that the sum of forces in the y direction equals 0. So what are all the forces in the y direction? Well, we've got Fa, that's going up, positive Fa, and we've got 1500 G going down, and we've got 15,000 G going down, and we've got Fb going up, which was 120,000. Okay, so if we just solve for Fa, Fa is equal to 1500 times 9.8 plus 15,000 times 9.8 minus 120,000. Okay, so Fa should equal looks like I'm getting 41,700, which if rounded to two significant figures would be about 42,000 newtons. So we've got 42,000 over here and 120,000 newtons over here. As I look at my notes or my PowerPoint, this was 44,100, but that was because on the previous slide, this had only been rounded to three significant figures, and it looks to me like it really should be two. So going with that two significant figure, it's 42,000 for FA and 120,000 newtons for FB. So that's using all three equilibrium. Well, actually, we didn't sum any forces in the x direction because there are no forces in the x direction. But just remember the three equilibrium equations: sum of forces in the x direction equals 0, sum of forces in the y direction equals 0, and the sum of torque about any given point in the system is equal to 0. If the system is in a state of static equilibrium, all three of those are true and can be used then to calculate any unknown forces, such as the reaction forces here at FA and FB.